TRE is cooperating with Professor F.C. Williams of Manchester University in investigation of circuit techniques for use in high-speed electronic computers. Two problems are being tackled at TRE. One is the provision of a storage system or electronic memory which will remember long strings of numbers for use in the later stages of a computation. And the other is a simple adding unit in which the numbers are represented by series of positive and negative pulses. Mr. R.H.A. Carter, who is working on the adding unit, will tell you something about the principles involved.
In this electronic computer, we simplify our problem by using what is known as a binary scale of numbers. Instead of working in tens, hundreds, thousands, that is, powers of 10, we work in powers of 2. This results in longer strings of figures to represent any given number, but as we use only ones and noughts, these can easily be represented electronically by positive and negative pulses. In other systems, only the ones are represented by pulses, 0 being no pulse. A fault could thus give a wrong answer by providing a string of zeros. The pulses are generated at the rate of 100,000 per second. Addition is effected in a series of ring bridge modulators, and the storage needed for transfer from one power of 2 pole to the next is obtained by charging a condenser on one pulse and releasing the charge when the next pulse comes along.
The brain of this system is an ordinary cathode ray tube, and the pulses representing any given number produce minute electrostatic charges which are stored on the fluorescent screen of the tube. The scanning beam traces out 32 parallel lines, and during each scan is intensity modulated in accordance with the digits representing the number to be stored. On subsequent scans, signals are picked up by this wire mesh on the tube face, and after considerable amplification are fed back to the modulating electrode so that continuous regeneration of the stored information takes place. When a number is wanted for a further stage in the calculation, the output from the signal grid is switched to the desired channel whilst the line containing this number is being scanned.
Manchester University, where anyone who urgently wishes to know whether 2 to the power of 127 minus 1 is a prime number or not, can be given the answer by an electronic brain in 25 minutes instead of by a human brain in 6 months. Setting the machine for this kind of problem takes a week. Then the brain is switched on and impulses passing to the computer make the actual calculation. The computer itself contains 1,500 valves. The brain at present is only in the experimental stage, the answer being read from a cathode ray tube. Later, an automatic keyboard will type the answer.
Since the beginning of recorded history, man has had to be able to count, to build his roads, his bridges, to formulate his theories of evolution, to build up the history of the planet we live on, and eventually he's had to busy himself with calculations about the universe itself. This is a galaxy, a vast cloud of whirling gas right out in space. And scientists wish to calculate how long it would take such a cloud of gas to condense into stars. Now, problems of this sort have a direct bearing on such things as nuclear energy and the possibility of space flight. But to do calculations of this type by the old pen and paper method would take hundreds of years. In fact, if a man started on a problem now, he'd hand it down unsolved for at least 10 generations before anybody came up with an answer. But nowadays, of course, we can turn a problem like this over to an electronic computer, and it will turn out the answer in about 500 hours. Now, we're at Manchester University to have a look at some computers. And the university, by the way, pioneered this sort of work. In fact, it built up the first commercial computer in the world. Now, there's nothing extraordinary about the look of one of these rather fantastic machines, but I'm going to ask Professor Williams, the director of the Electrical Engineering Laboratory, what's going on behind those variegated columns and panels.
We're looking down on the control desk of our Mark I computing machine. I've been looking down on it because although these machines can do the quite fantastic things that Mr. Reed has mentioned and many others besides, they are really essentially simple-minded devices. The program is called Brain in a Box. True enough, these machines can do many of the things that we normally do with our brains, and it can do them superlatively well. And true enough, it's in a box. But if your brain were no better than this machine, then you too would be shut up in a box, either because you were mentally deficient or because you were dead and buried in one.
Professor, you sound as though you're talking in riddles.
Well, the point I'm trying to make is that although these machines can in fact do these complicated calculations at lightning speed, they can only do them because we explain to them how they should do them. We make them do them. Left to themselves, they wouldn't even have enough sense to come in out of the rain.
Well, explain this a little more fully to me.
Well, suppose a girl is doing a calculation of some kind in the way we normally do them. It might be an income tax calculation or household bills or a scientific calculation. It doesn't really matter, the process is the same. She has to have a complete grasp of the problem that she's attempting. She has to understand what she's doing. All the time she has to keep track of what numbers she's using, what operations she's doing on them, and make sure she's working towards the solution she wants. She must in fact understand what she's doing.
But how is all this related to the computer?
Well, the point there is that it's hard to imagine that a machine could ever understand anything like, say, income tax. So we have to reduce the problem so that it can be done without understanding. Mm-hmm. And if you could come over to this model over here, I think we could do a little experiment which will explain this. I think with this model I can cause you to do a calculation without knowing what it's about, without understanding at all what you're doing throughout the process.
Okay, well, now what do you want me to do?
Well, I want you to move this control round one when I tell you to start, then read the instruction here and carry it out, move the control on one, read the instruction, carry it out, move the control on, read the instruction, carry it out, and so on indefinitely.
Right, is it all set? I move
it's
the
all
control
set
first.
to go now, right. Yes.
There goes the control, H to A. H to A.
That's right.
Then the controller gain, R to B. B is down there. Controller gain, multiply, well that's 90 if my arithmetic is all right.
Yes.
Controller gain, C to A, C to A, the controller gain, D to B, where am I, D, D to B, control again, subtract 70 Control again, C2O, C2O.
Now you see we've got Mr. Reed very busy indeed. He's started off now going round that wheel again, and he'll go on doing that like a mouse in a treadmill, turning out an answer for us here every time he goes around the wheel. I think probably we'd better rescue him or he'll be at it all night.
Well, what's all that in aid of?
Well, you've no idea what you were doing.
Not the slightest.
But it was very easy to do.
Yes.
What you were doing was working out a simplified payroll calculation, which is a thing this sort of machine is in fact used for. What you were doing, you were taking a number from here, which represented the number of hours a man had worked in a particular week. And then you took a number from here, which represented the rate of pay per hour. You multiplied these two together, and that gave you his gross wage for that week. Then you took a number from here, which was the total of his deductions for that week, income tax, national health, clubs, and so on, and you subtracted that from his gross wage, giving his net wage, let's say what he's to be paid. You put that here. Now, when you've gone all through those cards, I just take away this stack of cards from here, and those are all the wage packets that I have to make up. I've done nothing about it, you've done all the work.
Now, this then is the principle on which the computer works.
Exactly. It works by moving numbers about from place to place in the machine. These are labelled positions in the machine that it moves them about between. It moves them about in accordance with instructions that it takes one at a time in sequence, just as you did on this wheel. And
But could you have made me do a different sort of problem?
oh, very easily indeed. If you'd gone through exactly the same actions, but I had taken this wheel away and replaced it by this different one relating to a different problem, then without you knowing anything about it at all, you would have performed some totally different calculation. And that's just what we do with the machine. We put in a program that makes it do what we want. Without it...
Now, can we see how this works on the actual machine?
Yes, if we move back the machine over here. The first thing we have to do, of course, is to make up a program for the problem we want to solve.
Yes.
And first of all, we make this up in the sort of terms that we customarily use so that we can understand it ourselves in our own language. Then we convert this into the language of the machine. It uses a simpler language than we do. And what we do then is to punch this program, as we call it, up on paper tape with a special sort of typewriter. And it comes out looking rather like this, rows and rows of holes in a long length of paper tape. And we then feed that to the machine. We feed it in through an electronic tape reader over here, and that converts these rows of holes into electric impulses which are fed into the store in the machine.
I see, and the store in the machine corresponds to those stacks of cards, the H's and the R's and the D's that I was using over there.
And of course also to the instruction wheel. We have to put the instructions in as well. That all goes into the store, and of course there are many more places in a machine than the three we had on the model.
Yes. Now, what is the problem that you're going to feed into the machine?
Well, that problem we just put in was asking the machine to calculate the sum of the square roots of all the numbers from 1 to 50. Well, now, the square root of 4, of course, is easy. That's 2. The square root of 9, easy again, 3. But the square root of 13 isn't quite so easy, and neither is the square root of 49. And the machine has to work these out in great detail.
Now, the point is that you, all these figures are, this information is turned into a series of electrical impulses.
Yes.
Now, let me see if I've got this correct. All figures can be represented by electrical impulses, and all, say, your multiplication symbols and so on the same.
Yes.
As they come up against each other, they react.
Yes, yes.
So that if you have, say, a symbol, an electrical impulse for a 2 and a 4, and also for a multiplication symbol, the automatic answer is 8.
Well, they're arranged so that it will be, yes.
Right. Now, what are we going to do now?
Well, I thought now we would run this problem to give you some indication of the sort of speed at which these machines
Well, look, can we
work.
put the stopwatch on it when
Oh,
it
yes.
starts, just to see how it does work?
Shall we start it now, shall we?
Yes.
Right, start now. The whole point about these machines, of course, is the speed at which they operate. You took about 10 seconds per step on the model. This is doing about 1,000 steps a second, and some of the newer machines, of course, do up to 10,000 and even more steps of this kind per second.
Ah, is that the signal?
That's the signal now that the problem is complete.
20 seconds.
Yes, 20 seconds, and we have the answer just coming out of the machine now.
What is the answer?
There we have the answer, 239.03580.
Well, I'm sure I wouldn't have known the first way to set about solving that one.
No.
But of course, you don't use it just for this sort of trick
Oh,
work,
no,
do you?
indeed. That's just a demonstration for you. It's time now that it got down to serious work.
Well, is this some serious work coming up?
Yes, these people have heard the hooter calling for more work and have come along from the meteorological office to put a weather forecasting problem onto the machine.
Now, how are they going to operate?
Well, she's putting the new tape in for the new program there, you see. And if we can have this camera well in and the lights down a bit, please, then on this tube we see information going into the store of the machine from the paper tape. On this tube we see multiplier and multiplicands for multiplications, putting answers from those multiplications onto this tube. And meanwhile, this tube is storing the number which tells us how far we've got in the program. That's the number of places round the instruction wheel.
Professor, the one point strikes me about this. This is essentially a mathematical machine, but it's been devised by an electrical department. Now, I assume that this means a great deal of cooperation between different departments of the university on a research job of this sort.
Oh, yes. You must remember that about 11 years ago when we started on this work, there weren't any machines of this kind anywhere in the world, and the problem of developing them was essentially one for cooperation between mathematicians and engineers, and we worked very closely with our mathematics department here. But naturally, of course, we built the prototype in the electrical engineering department, since it is an electrical engineering device. That's the picture of it there, actually. You can see that it's a sort of sticks and string device, a sort of thing research people make, and it has to be developed a good deal, of course, before it can be used as a computing machine. It has to be properly made and so on. And for this purpose, we enlisted the aid of a local firm who collaborated with us in the design of a proper, usable computing machine. And we've some film taken in the factory, which shows what goes into these machines and just how they're built. You can see coming up there the black cylinder, which is coated with magnetic powder and rotates at 3,000 RPM.
Now, is that the memory drum? What does it store?
It stores electrical impulses. Electrical impulses go into it, and they're converted to magnetic marks on the coating in very much the same way as in magnetic recording of music.
And are those the drums again?
That's a set of drums ready for test. You can see the reading heads, those black knobs. They're spaced apart, and each one records on a different peripheral track round the drum. There's a close-up of the heads showing the spacing.
Now, there must be a tremendous amount of very fine precision work of this sort, isn't there?
In this particular part of the machine there is, because these magnetic heads, like that one the girl's soldering up there, operate a fraction of a thousandth of an inch away from this drum that's rotating at 3,000 RPM, and that clearance has to be maintained. And then again, the reading and recording gaps have got to be highly accurate, because the marks that we put, the magnetic marks we put on the drum, are only a few thousandths of an inch in size. Here we've got some soldering in of components. The components, of course, of a computing machine are very similar to those that you would have in a television set. The only difference being that whereas you might have a dozen valves in a television set, there would be 2,000 or 3,000 in a big computing machine. Apart from that, valve resistances, condensers, and so on.
I suppose this is going up to the assembly point, is it?
Yes, they're assembling racks here. You can see there on that picture how closely the components are packed, and remember there are many racks that size in each computer. That's a sub-assembly there on test, you see, and on the next picture here you can see the the valves at the top there. He's just putting that rack into a computing machine. Now he's checking that the thing works properly with the...
It's reading off the performance.
That's right, to see that it's working correctly.
What's that tape in the background?
Well, that's much more conventional magnetic tape, as used for sound recording. We use it for additional memory purposes.
Now, what about the sale of these machines, export, for example?
Oh, well, these machines are sold to industry, to universities, to government departments. They've been exported to Canada, Norway, France, Italy. The latest order's going to Germany. This is the control desk of a machine like the one we have in the university. And I think we might now go back to the university to meet Dr. Kilburn, who is the reader in electronics and who is in charge of the computing machine work in this department.
Well, I've come over here into the Mark II room to have a talk with Dr. Kilburn. Now, how does the Mark II or Mark I differ from the Mark II?
Well, the basic principles of the two machines, those principles are the same. But whilst we were building the Mark I, and whilst we used it during the 5 years or so that we've been using it, it became clear that we could build a better machine and improve the Mark I design in certain ways. These improvements have been incorporated in this machine. In particular, we have increased the size of the memory, and we've made the machine easier to use by improving the language which the machine uses and bringing that language closer to that used in everyday life. The most spectacular improvement, however, is that this machine is 30 times faster than the Mark I machine, so that if we did the problem about the square roots, which you did on the Mark I machine, that you will remember took about 20 seconds there. On this machine, it would take about a third of a second.
Now, are any developments, further developments possible?
Oh, yes. In many places, designs and plans are afoot to build machines about 100 times the speed of this particular machine, and these plans are made possible by normal scientific research and development on computer components. For example, if we take one component, we see that a valve from the Mark I machine is quite large as we move on in comparison with a valve from this machine.
Yes.
Valve development during the years has decreased the size. The performance is at least as good. A most important change came with the invention of the transistor, which you see here, and machines now being planned will use these very small components which do some of the work of a valve in very large numbers, perhaps 10,000 or so in each machine.
Do you think you'll be able to go on increasing the speed of computers indefinitely?
There seems to be a limit to this set by the speed of light. Electrical pulses can't travel any faster than light, and in a machine of this size, electrical pulses starting at one side of the machine have got to travel quite a large distance towards the other side of the machine, and when they arrive at the other side of the machine, they're rather later in time than when they started out. We can demonstrate this by putting an impulse, an electrical pulse, through a cable. Now, on the table there you see a cable, and on a cathode ray tube screen we shall see pulses which are similar to the pulses existing in this machine here at the moment. Those two pulses, one appearing above the other, could, for example, be added together because they occur at the same time. But if we take the pulse on the bottom trace, which you can see there as a kink in the lower trace, and put it through a cable, then you will see that the pulse is displaced to one side and occurs later in time. Now, the pulses, although displaced, still overlap a little. The back of the top pulse overlaps the front of the bottom pulse, so that we could still, in extreme case, perform an addition, because they're not quite too terribly displaced yet. But if we contemplate building a faster machine, then we shall have to decrease the width of the pulses, and this we can show now. The width of the pulses would then be about 1/10,000,000th part of a second. That is to say, the time duration of each of those pulses, which you can see, is less than 1/10,000,000th part of a second. Now you can see that something quite significant has taken place, because the pulse on the top trace is complete, quite complete, before the pulse on the bottom trace occurs, and therefore we are not any longer able to add these two pulses together. Now, we can get around this in various ways, but the most important way is to shorten the length of the cable. In other words, to contract the size of the machine so that the wires in the machine are not so long.
Now, what are going to be the limits of this sort of development?
Well, it's always very difficult to specify ultimate limits, but we can give some idea of the trend by comparing machines of the present day and of the future with the Mark I machine. The machines contemplated at the moment are going to be between 1,000 and 10,000 times as fast in speed of computation as the Mark I. But if we go beyond this and contemplate machines 1,000,000 times as fast as the Mark I, then we should have to compress the whole of the computer into a box
That size?
about this size,
Yes.
because the time delay in passing from one point of the computer to another would have to be so short.
Right, well, that's very much for the future, but what about the present? Now, how much do these machines cost?
Well, this machine is reasonably typical. They vary a little in price. It would cost nearly £100,000.
Nearly £100,000. If I came along to hire one to do a job of work, how much it would cost to hire?
Rental varies again, but the rent per hour is about £75. That is to say, £75 per hour.
£75 an hour for using this machine. Well, there you are. That shows what there can be done in the way of computer work for industry, how much it's going to cost them to hire these things out. And of course, computers are being used for all sorts of things, and we'll show you one or two examples. Now, this, for example, is a transformer, and computations can be made with the computers for this type of work. The computer can calculate critical speeds on turbine shafts. They work out the stresses and strains on steel girder buildings. Now, this, for example, is the new BBC TV centre in London. And in aerodynamics, they calculate the flow of air around the wings of planes. But earlier on in the programme, we saw some people from the Met Office who were working on one of the computers. And we're all, of course, interested in weather forecasting, particularly at this time of the year. Now, Mr. Bushby, what sort of work are you doing on the computer here?
Well, we should get the answers to the calculation that you saw me feed into the computer a little later on. But our problem, briefly, is this. The map is covered by lines joining points at which the barometric pressure is the same. All points on this line, for instance, had an air pressure of 1,016 millibars on that occasion. The lines are drawn by estimation from reports of pressure from hundreds of observing stations. We also have to know what the pressure situation is in the upper reaches of the atmosphere. And here you see Miss Whiteman reading off values of pressure from a chart which shows the pressure and wind distribution 18,000 feet above the ground. When we've obtained such a map, we have to estimate what tomorrow's weather map will look like. And this is usually done on the basis of experience of what usually happens in a case like this. And when we've got tomorrow's weather map, we have to deduce what weather is likely from it.
Now, when you use the word deduce, I gather that means that you can't be absolutely sure mathematically of some point.
Well, that's true, but air is a fluid, and its movement is governed by the laws of motion of fluids. And these laws can be represented as equations, and they look like this.
Well, they look frightfully complicated.
Well, if we replace certain terms in these equations by actual measurements of pressure, and then solve the equations, we can arrive at tomorrow's weather map more scientifically.
Now, how long would that take to do by paper and pencil, that calculation?
Well, it would take about 3 years, but it can be done in 3 hours on the Mark I computer.
And what sort of information would you have to feed into the computer?
Well, we read in numbers which have been extracted from charts, and I've got an example here of an actual situation that we produced a forecast for. This is a surface pressure map that we started off with, and you'll notice a depression in mid-Atlantic where the pressure was 1,008 millibars. Now, the machine produced a forecast like this for the next day. And here you see a depression where the centre pressure was 996 millibars over northern England. And in the middle of the Atlantic, we have now developed an anticyclone. This chart shows what actually occurred. You'll see the depression very close to where the machine forecast it to be, although the machine forecast it to be a little too deep. And here is the anticyclone that the machine forecast, although it is not as intense as the machine forecast.
Now, what about this problem we saw you working on earlier on in the program?
Well, I think we've just got some results through now, actually. Ah, yes. Since the program started, even using the Mark I computer, we've only had time to produce a 3-hour forecast so far, although this has involved the machine doing something like 1 million additions, subtractions and multiplications.
1 million additions, subtractions inside about 20 minutes?
Yes, and this would only have taken about 1 minute on the Mark II computer.
Well, now, when you get your own computer delivered, does this mean to say we're going to have error-free weather forecasts?
Well, even if we could produce error-free weather maps, and we're still a long way from that, there's still the problem of deducing the weather from the weather map. So we haven't been able to remove the human element altogether.
Well, thank you very much, Mr. Bushby, and let's hope we have some really accurate weather forecasting in the future.
Right, thank you very much.
Well, there you are. This is what I'd call a double-barreled example of research work. Because here, as Mr. Bushby's shown, you have scientists using the computer to improve the techniques of research work in their own jobs, in this particular case, so that we can get weather forecasts which are mathematically as accurate as possible. But computers are also well and truly launched on a practical basis. Calculations made on computers help to speed up the development of atomic energy. They're used on very big engineering projects such as the St. Lawrence Seaway in Canada, and they're now being used by commercial houses for all sorts of costings, wages and so on. But I think the main asset at the moment of the computer is this. Scientific developments are speeding up at a terrific pace. The basis of most of those developments is a mathematical one. Now, the old drudgery of pen and paper mathematics simply would not stand up to the speed and the pace of these developments. But here you have something that will, a computer, a man-made machine. Good night.
An Atlas at Manchester. Using thousands of circuit packages like this, the world's fastest and most powerful computer takes shape, built at the Manchester Computer Factory of Ferranti Limited, and destined for the Computing Machine Laboratory of Manchester University. Long collaboration between Ferranti and the university has already produced the world's first commercially available computer, the Manchester Mark I, then Mercury, and now Atlas. Package shelves being assembled. Many parts of Atlas must be handmade, for automatic methods of construction are not exact enough to ensure the complete reliability that must be achieved if Atlas is to function as it should, with a speed and complexity that take current components and methods of construction to the limits of their possible performance. If only one part were to fail, the whole computer would be out of action, for with a computer, unlike other machines, there can be no operating at reduced efficiency. The circuits seen here being assembled and later interconnected represent great advances in design and put Britain in the forefront of world computer technology. Under the leadership of Professor Kilburn of Manchester University, new circuit techniques, including a new method of fast carry-digit propagation in the adding circuits, extremely rapid access to storage, and extensive parallel operation, have all been combined to give Atlas an operating speed of about 1 million commands a second, the fastest speed ever achieved. This speed is the limit of conventional components and methods of construction, because signals cannot travel faster than light, which only travels a foot in a millimicrosecond, and this is now a limiting factor in design as operating speeds increase. Finished packages of many types, all using transistors instead of valves, and all carefully assembled on printed circuit laminates with hard gold contacts, varnished and tested, are the building bricks from which much of Atlas is made up. In the central bays of the computer, there are 1,200 of them. These bays form the central computer, and they contain the arithmetic unit, the control unit, and the index store. To make up a complete Atlas, many other bays, concerned both with computing and with power supplies, have to be added, together with a great variety of peripheral equipment, so that altogether an Atlas installation will occupy upwards of 2,000 square feet of floor space. However, Atlas is big and complex not to break a record, but to meet a demand. Current computers cannot cope with the work, great both in quantity and complexity, that needs to be done. But Atlas will provide about 1,000 times as much computing power as most medium-sized computers, and at a cost per computing operation that is less than on any other computer. First among the important design features of Atlas is the way in which the flow of information within the computer is organized in new ways to ensure maximum utilization of the computing power available. A supervisor program, permanently stored in the novel fixed store of Atlas, automatically controls the flow of work through the machine. Time sharing on Atlas enables any number of programs to be handled concurrently, and the supervisor program continually reviews the priority to be accorded to various jobs and allocates store capacity and peripheral equipment between them in such a manner that the most efficient working of the system as a whole is assured. The supervisor program also organizes transfers between various levels of storage, say from the drum store to the rapid access core store, entirely automatically, so that the user, when programming, need give no thought to the necessity for store transfers and may look on Atlas as having a single level store. The supervisor program also greatly simplifies the work of the Atlas operators by carrying out automatically all the scheduling of work being put on the machine. If programs and data are set up on any available input machine, the computer will find the ones it needs entirely automatically. Next, by providing several distinct paths of access to different parts of a high-speed core store, it has been possible for commands to overlap. In practice, this means that as many as 3 consecutive commands may be in different stages of execution at the same time. Lastly, many of the jobs which in other computers require extensive special circuits, for example to control associated punched card machines, are dealt with in Atlas by internal programs stored in the fixed store and obeyed by the main control unit of the computer itself, an advance only made possible by the very high computing speed of Atlas. The central bays of Atlas leave the factory for the university, where many departments and many organizations with problems in mathematics, physics, chemistry, biology, agriculture, economics, statistics, production planning, costing and engineering, problems that will take anything from a few seconds to a few hours of Atlas time, will use Atlas. Here, in the room at the university, where the first Manchester Mark I, 1,000 times slower than Atlas used to be. Following on the university Atlas will be other Atlases for other purchases. They will be programmed by hundreds of people, particularly if they are linked to remote users by data links. Programs for Atlas will arrive written in machine language, Mercury autocode, Nebula, and in other automatic programming languages. Atlas itself has been programmed to compile a compiler for any autocode. At the university, where Mercury is already in use by almost every department, Atlas will present immense new opportunities. It will be particularly used for nuclear research, for radio astronomy, for X-ray crystallography, and for linguistic analysis. Dr. Kilburn, responsible for Atlas design, seen here with some of the Atlas team, will also use the machine for further research in computing itself. The complete university installation will comprise computer bays, power supplies, 16,000 words of course door, 8,000 words of fixed door, 4 magnetic drums, 8 magnetic tape units, card and tape readers and punches, a hammer printer, and a graphical output plotter, in all making a system that will bring cheap, large-scale computing to a new world of computer users.
Hello there, Nolan Pritchard reporting from Britain. Ask me to name the one thing that's going to drastically change your life and mine in this century. And today, I can point right to it and answer this. It's a computer. There comes a point at which sheer speed of discovery can change our whole approach to understanding. And the computer opens up this new world. This one, named Atlas, just happens to be the latest, the fastest, and the most powerful in the world, that's all. What most computers today can do in 10 minutes, Atlas can do in 1 second. And as of this week, when Atlas comes into service, computer capability in Britain is doubled. There are only 3 types of machine that can even touch Atlas, and they're being built now in America and Japan, while even more Atlases are coming off the line here in Britain. Atlas doesn't just do better what other computers can already do. It can occupy itself fully in its spare time, automatically switching over to its homework if it happens to be too quick for its operator. It continually lets you know what it's working on and tells you if it's made a mistake. Atlas can do simple arithmetic at up to 1,000,000 operations per second. Most impressive, there is already a demand for a machine with this capacity for work. This is not just for special, occasional jobs. Most computers now are swamped with work, and only something as big and fast as Atlas can tackle the kind of calculations now required for space research and atomic physics. Atlas will help the Meteorological Office study patterns of weather, and later it may even try its hand at weather forecasting. There are plans for Atlas to study French literature and analyze vocabulary. It may even do language translations. For all this, the computer is no equivalent to an electronic brain. More accurately, an electronic idiot by human standards, according to Professor Tom Kilburn of the University of Manchester. Incidentally, he designed the first computer made commercially available in 1951. You may ask, why build the world's fastest computer for use in a university you've hardly even heard of, the University of Manchester? Well, first of all, Professor Tom Kilburn happens to be here. And secondly, you just don't know the University of Manchester. It was here that Jodrell Bank, the world's first radio telescope, was built. When Russia's Sputniks went up in 1957, Manchester had the only facilities good enough to track them accurately. For a time, Russian scientists were almost commuting between Moscow and Manchester. And America's Project Mercury has made extensive use of the telescope. The new atlas will soon be linked to the computer at Jodrell Bank. The Industrial Revolution began here in the north of England, and Manchester hasn't looked back since. It's an old saying that what they do in Manchester today, they'll be doing in London tomorrow. And it's true, the University of London doesn't get its atlas for another 2 years. Nolene Pritchard saying goodbye for now from Manchester.
Manchester University, where anyone who urgently wishes to know whether 2 to the power of 127 minus 1 is a prime number or not, can be given the answer by an electronic brain in 25 minutes instead of by a human brain in 6 months. Setting the machine for this kind of problem takes a week. Then the brain is switched on and impulses passing to the computer make the actual calculation. The computer itself contains 1,500 valves. The brain at present is only in the experimental stage, the answer being read from a cathode ray tube. Later, an automatic keyboard will type the answer.
Okay, well, it's now 14:02.
Maybe not then.
So on the dot does not work.
Yep. But I'm still going to give him the palette. I'm still going to give him the palette. Yeah, no, it's fine, it's fine. So that's... Okay, it's not going to start until it starts anyway, isn't it?
Yes.
Right, okay.
Yeah.
Well, I'll just sit here.
People coming in, so actually it's not such a bad.
I'll be waiting on the wings, I think, so. I don't want to stand in the way here, so I'll wait in the wings, and once I see it, I'll come.
Yeah, yeah, okay,
Cool.
that's good. I could have jumped up and introduced him, that's fine.
Whatever works, yeah, whatever works, yeah.
Okay, if you're ready, we'll get
Yeah,
started.
anytime.
Okay, I think we're close to starting. Okay. Right. Excellent. Okay, good afternoon, everybody. Okay, good afternoon. Good afternoon, distinguished guests, ladies and gentlemen. It is a pleasure to welcome you to this IEEE Milestone dedication ceremony to unveil the plaque to mark the invention of the Manchester Code in the late 1940s. I'm Tom Thompson, the chair of this meeting and also the general chair of the Intermag 2026 meeting, which is happening all week in Manchester Central. And we're delighted to be joined by so many distinguished guests from that conference. The conference also includes an outreach event, if anybody is local, is interested, in Mosey on Saturday to demonstrate magnetic technology, past and present. Next slide. Oh, I'm in charge. It's apparently me. Okay, good. Now we've mastered the technology. Okay, the thing that we have to say here is many thanks to the proposers of this milestone. The proposing an IEEE milestone is a necessarily rigorous process, requires dedication and meticulous attention to detail. And it's a real pleasure and privilege to thank Professor Jim Miles from this department, the late Professor Simon Lavington, and Professor Roland Abbott from... oh, we've got hecklers! It's a real pleasure to thank all involved with this milestone dedication, because putting it together, I saw how much work Jim actually took to put that together, and it's a real tribute to his and to everybody's in the IEEE's dedication to put that together. So I'm really delighted to thank you for doing that. The programme this afternoon is fairly full, so I'm going to talk, fortunately, for only a very short period of time, and we have this full agenda, and the key moment is where the plaque is going to be presented by the 2024 President of the IEEE, Tom Coughlin, here to the university for the milestone, and that you can see that it's set up there to go. We are going to conclude 3 technical talks this afternoon, one from Jim on the development of the milestone, of the sort of history behind it, and then its impact both in terms of data storage and in terms of communication. So those are our 3 technical talks, and then at the end of that we will have a reception just upstairs from here, and I know that's the point everybody wants to. So now, rather than listen to me, it's my very great pleasure to introduce Professor Duncan Evertson, Vice Chancellor and President of the university, to say a few words about the university. Duncan.
Thanks, Tom. I'm very happy to become Vice President of the university. If any, the job is yours. So look, it's a delight and great honor to be here this afternoon. And in many ways, it represents one of the reasons I feel unbelievably privileged to be in this role, because Manchester is really in many respects, the birthplace of this extraordinary transformative technology that we are now experiencing and living through at the moment. I've literally just come back from a weekend in Hong Kong where there was a dialogue between US, Chinese, and European colleagues across various institutions thinking about the future of AI, given the incredibly difficult geopolitical moment that we're in. And there were many references to Turing, to the origins, indeed, of the Manchester Code and Baby, and the extraordinary explosion of the technology from the moments that began here in Manchester. There really were sort of pinch me moments over the course of the weekend when this occurred. And I did have to point out to the people that, of course, Turing wrote that famous test paper for the philosophy department colloquium at Manchester. And as a philosopher, I always like to remind people of that, especially in a room full of computer scientists. But we need that multidisciplinary approach even more now. So can I thank the IEEE for this incredible honor? We're very grateful for the recognition. Can I also declare that our tendency to be modest about these things is now officially over, and we will be bragging and putting the plaque on social media like you've never seen before in the weeks and months ahead. But I do also want to pay tribute to all the researchers and all the colleagues who've done so much and continue today, indeed in this school, in this faculty, in this place, to really advance our understanding, not only our understanding of this technology, but the responsible and ethical deployment of it as well, which is also at the heart, I think, of the Manchester story. You know, I don't know, I'm sure many of you have, but I not too long ago, I went to the Computer History Museum in Palo Alto in California, and if you go into those early rooms of the Computer History Museum, it's really the history of Manchester. And then the Americans sort of take it away from there. So there's a lesson for us to learn from that. But really, again, thank you so much for this extraordinary recognition of the groundbreaking work that was done in this place, in this city, not just in the 1940s and before, but continues to be done today. And I think we really see this, not only a validation of that work, but a real inspiration and encouragement to keep going and to put Manchester once again at the heart of this extraordinary technological revolution, but also at the heart of it in the right way, in the thoughtful, reflective way that it began. So thank you very much.
That's great. Thank you very much, Duncan, for putting that into context. Our next speaker this afternoon is Tom Coughlin, who was president of the IEEE in 2024, and will talk about the Milestone program.
I shall.
Tom.
Is my mic on? Sounds like it. Yeah, good. Okay, thanks. Let's see, that's not me. Here we go. Okay, so thank you, Tom, for inviting me, and Jim for putting everything together here, and all the rest of you for being here. So IEEE is the world's largest technical professional organization, and we've got a mission, which I think is kind of a cool one, which is to foster technology and innovation and excellence for the benefit of humanity, or technology for the benefit of humanity. And the story of IEEE actually begins back in the 19th century. At that time, scientists and engineers began to harness electrical power, connecting the world via transatlantic cables, building ringing telephones and switch lighting systems. Electricity was gaining global influence, and in the spring of 1884, a group of industry professionals met in New York City, and they had a dinner. And at that goal, they agreed upon a goal, that they would use their knowledge and influence to benefit humanity. And that led later in 1884 for people like Thomas Edison, Alexander Graham Bell, and others to found the American Institute of Electrical Engineers. In 2012, the Institute of Radio Engineers was formed with a focus on new industries of wireless technologies and electronics. And on January 1st of 1963, these two groups joined together to create what's the Institute of Electrical and Electronic Engineers, or the IEEE. So the IEEE today has over 500,000 members in over 190 countries. We have 39 technical societies and 8 technical councils. These are all different. For instance, we have the president of the Magnetic Society right here, Ron, and they work in various fields and work together in many ways. We're a publisher of a great amount of the world's technical literature. We have over 1,000 active standards, traditional ones on interoperability, et cetera, but new ones on, for instance, ethics and AI, ethical practices in AI, for instance. We have published, again, a lot of transactions. We sponsor over 2,000 conferences in, again, over 190 countries. And continuing education resources, we're also involved in global public policy and other activities as well. So IEEE is a public charity, and part of what we do is to provide learning and education, particularly for scientific purposes. And our activities are all tied to that mission we spoke about before, for advancing technology for the benefit of humanity, which helps better demonstrate the great impact that IEEE, our members, and engineering technology have on society. These activities encompass efforts in such areas as community building, education, ethics, history, humanitarian technologies, public policy, as well as sustainability. And these activities play an important role in demonstrating the great impact that IEEE members have on our society. Our public imperative activities help us to increase the public's understanding and appreciation of our various fields of interest and highlight not only our members' technical expertise, but also their desire to use their skills and knowledge, again, to benefit humanity. So we're more than electrical engineering and computer science. We look at the big picture. We see society as a whole. And to me, again, this is an awesome mission, and I was glad to have the opportunity to help to promote it. So exploring the contributions of key figures, you know, with the history of major people in our, who have shaped electrical technologies and computer technologies. Michael Faraday and his discoveries of electromagnetism, Grace Hopper, the pioneer of computer programming, as well as the challenges that these people overcome, offer valuable context for current and future innovators. A great understanding and appreciation of historical contributions of IEEE's fields in engaging in open dialogue with the public can help build a more sustainable, efficient, and technologically advanced future. Public trust and engagement are essential for the continued progress and acceptance of technological advancements. By revisiting past successes and failures, policymakers can better anticipate the consequences of new technology, advances, and develop policies that foster innovation while also ensuring public safety and environmental sustainability. So history serves as a testament to the power of human ingenuity and collaboration. By studying the evolution of electrical engineering and related technologies, we can identify patterns, reflect on what worked well and why, and analyze what went wrong as well. In fact, making mistakes is an important part of making progress, and therefore build upon existing knowledge in order to create new technologies, whole new industries, and whole new ways of looking at the world. Since its inception, IEEE has had a standing history committee concerned with maintaining its legacy, the legacy and heritage, rather, of the organization and its members, and the related professions and technologies. The IEEE History Center preserves, researches, and promotes the legacy of electrical engineering and computing through its numerous programs, like the Milestone program. The IEEE Global Museum brings traveling exhibits focused on the history of electrotechnology to IEEE members and to the broader public. The museum promotes awareness of how technological progress unfolds over generations and how engineers and researchers can build upon past achievements to improve people's lives. IEEE Reach, which is a program with the History Center for pre-university teachers, provides resources, free resources to promote, that's help people to understand science, technology and engineering, and their social and human contexts. These resources provide students with an understanding of technologies, including how they have shaped society, and in turn, how society has shaped them. So IEEE's oral history program collects spoken memories and personal commentaries of historical significance through recorded interviews. And there's various programs they have for doing this. There are nearly 900 interviews which are available. You can take a look at them at ethw.org. And as an IEEE past president, at some point they're going to do an interview of me too. But I also helped to do some interviews of other people in the past. They had a volunteer interview program that was set up. IEEE milestones, what we're here for today, are more than just plaques. You'll see one in just a little bit here. They are pillars of legacy, platforms for learning, and symbols of an impact that the technologies have had. They educate the public. These technologies serve as public educational tools, helping communities understand the significance of local contributions for global progress. They inspire future innovators by showcasing breakthroughs across disciplines, from computing to biomedical engineering. These milestones connect past achievements to future possibilities. They remind students, researchers, and professionals that bold ideas can have a lasting impact. They foster pride and engagement. Milestones strengthen IEEE's identity and visibility, especially at the section level, where local members feel a direct connection to the legacy. Today's celebration marks the 22nd, though I think somebody else had 23rd, right? Yeah. 23rd milestone for the UK and Ireland section. These include the earliest IEEE milestone, which is Benjamin Franklin's work in London, which I have been to thanks to some folks here. Manchester Code was invented for the storage of data in a magnetic drum store of the Manchester Mark I computer. It became a standard for computer magnetic tapes and floppy disks and was used in digital communication, including, for instance, the furthest communication mankind has done so far, the Voyager 1 and Voyager 2 spacecraft, as well as in early Ethernet networks. It found wide use in radio frequency identification, RFID, tags, many control network standards, and domestic remote controls found in millions of homes across the world. This truly is an ubiquitous technology today. And as someone who has worked in the field of digital storage industry for getting close to 50 years, I can say that the Manchester Code and its descendants have enabled the capture and retention of vast amounts of information, as well as industrial and consumer applications, and especially communications that define our modern world. So with this, I want to say that what we're here today to recognize is the impact that some developments, technologies, hard work that a group of people did made a lasting impact. And we're here to help preserve that heritage. And we are, in fact, the stewards of our history, the stewards of what has been done and what will be done. These things have, I believe, enduring relevance, show that people can make things that never existed before, that create new wealth, new opportunities, and the historical impact is to be recognized here today. So I'd like to go once again share my sincere gratitude to all the leaders from the IEEE UK and Ireland section for organizing today's event and for inviting me to come. I applaud your efforts to celebrate and to safeguard the contributions to society made by electrical, electronics, and computer engineers and computer scientists, and the strides made by countless technologists as they seek, again, to advance technology for the pursuit of happiness. Sorry, the benefit of humanity. By celebrating the pride and prestige of our professions, we demonstrate how engineers, scientists, and technologists contribute to our global community and have helped to build today's technologically innovative world. They have shaped the trajectory of technology, our communities, and institutions. Their stories, their lessons should be told and retold as long as human beings strive to make this world a better place. Thank you for the chance to talk to you today.
So I would now, I think we move on to the stage of presenting, yes, presenting thing. So I would like to invite Tom Coughlin and Duncan, in behalf of the university, to receive the plaque.
Do I pull the short one? Okay.
I think we have to be organized for photographs.
We do. Okay, here we go.
Yes.
So first of all, I give you this plaque, which you guys paid for. That you may
typical.
Yes, that you
typical Americans. Yeah.
That you may commemorate this great invention, and it's all the advances that has helped to promote. Whoops, we're feeding back somewhere. Should I do it?
Well, I don't think it might be me.
Okay, ready? Okay, here we go. Yay!
Fantastic.
Thank you, sir.
Thank you.
Do we want to read the inscription? I think I will try.
Would you like to read it, sir?
I will try and read it. Yes,
okay.
Without making too many mistakes. The plaque reads, for those who can't see it, IEEE Milestone, Manchester Code 1948-1949. At this site in 1948-1949, Manchester Code was invented for reliably encoding digital data stored on the Manchester Mark I computer's magnetic drum. It became a standard for computer magnetic tape and floppy disks and was used in digital communications, including Voyager's 1 and 2 spacecraft, and earlier Ethernet networks. It has also found wide use in domestic remote controllers, RFID tags, and many other control network standards.
Good job.
Thank you. Okay. So it is now my pleasure to start the technical part of this afternoon's activities. As I mentioned at the beginning, we have 3 talks dealing with both the milestone and its impact in data storage as well as communications, which is covered obviously in the citation on the plaque. So it's my very great pleasure to for the first speaker to be Professor Jim Miles, who proposed the milestone and did all the hard work for this. So it's only fair and fitting that he is our first speaker. Jim, please.
Thank you, Tom. So, as the slide says, I'm going to talk about the invention of Manchester Code. So basically, I'm going to talk about the circumstances within which Manchester Code was invented, the reasons why it was needed, and what it was first used for. And then the next 2 speakers are going to talk about the impact that it had in the future on data storage and then in communications. Okay, not this clicker then. Oh, it is. Okay, sorry, it's just slow. Before I start, I would like to just say a few words about Simon Lavington, principally because in 2022, we had 2 milestones awarded, one for the baby, which Simon was the lead proposer, and one for Atlas and virtual memory, for which Roland was the lead proposer, and I tagged along. When we got to the end of that, Simon pulled me to one side and said he thought that perhaps Manchester Code might be a good third one, and then went on to say that unfortunately he didn't really have time to do it, and looked pointedly at me. So here I am. Simon, I'm very glad to say that Simon did live to hear that this milestone had been approved and had gone through the final stages of IEEE approval. But sadly, he didn't make it here today. Simon spent 50 years of his life raising the profile of the history of computing in Manchester. And in the very short period of time when I've been trying to cover that, he was enormously helpful to me, phenomenally patient with my endless, tedious emails asking him minor points of detail. So, as a personal tribute, this talk is really for Simon. So, as I said, I'm going to talk about the circumstances within which Manchester Code was invented, why and what primarily, and why it was necessary, and right at the end I'll tell you about what it does and what it did. So this is essentially background. Sorry. So the story starts with the baby computer. I'm not going to give you the whole story of the baby, but in brief, FC, or Freddie Williams, in 1946 invented a way to store digital information on a cathode ray tube. He brought Tom Kilburn and Jeff Tootle to work with him, and together they built a working CRT store in the university. They then needed to test it, and the best way to test it was to build a small computer that would try to run a program. And if the store actually succeeded in running a program, then they knew that the store worked. They proved that the store worked. And that was what was originally called the small-scale experimental machine, or came to be known as the Baby. And Baby ran its first program on the 21st of June, 1948. It's worth spending a little time talking about the memory of the Baby. The Baby, when it was first created, had one cathode ray tube, which you can see in the middle of this image, which stored 32 32-bit words. So it had a 1 kilobit memory. All right, 1 kilobit, it's tiny. They very quickly expanded this by growing the word length to 40 bits. So its memory capacity increased to a massive 1,280 bits. But it was still only 32 words, so it really not very much direct help. So by 1947, it's documented that by 1947, Williams and Kilburn knew that they would need more memory. So this is 7 months before the Baby actually ran a program. They knew they would need more memory. The ideal solution, I guess, would have been to have lots more CRTs, but that would have been very expensive in power, very expensive in space, very expensive in money. This was just after the war, and equipment was hard to come by, and a lot of this stuff was basically built on a shoestring with whatever they could scavenge from wherever. So that really wasn't a practical solution, so they needed a second-level memory. So they had to think about what they could use as a much bigger memory which they could use to expand the capacity of the machine. And the solution that they hit upon was magnetic drum stores. Now, I have to be absolutely clear at this point, they did not invent magnetic drum stores. As far as I know, they did virtually nothing innovative in magnetic drum stores, they just built one. Magnetic drum stores had been discussed actually before the war, but they were being quite actively discussed in the USA, 1945 to 6. And Williams visited the USA twice, once in 1945, again in 1946. visited a lot of labs across the USA. It's very likely that he heard people talking about magnetic drum stores whilst he was there. And there was a lot of active work going on in the USA very early on after the war in drum stores. I'm just going to show you some examples. These are not actually directly related to the invention, but it just gives you an idea of what was going on in computer development at the time. Probably the best example for this is Engineering Research Associates, which is a company that was set up to do research and develop systems for the US Navy. And they began research on magnetic drums as early as 1946. And they had an experimental drum store working sometime before June 1947. There's a published paper from them in June 47 where they describe a working system. So at some point before that, they had a working system. So I think that that is probably the earliest working magnetic drum store in the world. And their drums went on to be used in lots of different machines, the MIT Whirlwind particularly, but also various US Navy machines. I rather like this advert. This is an advert for ERA. Two things about this that I like. Well, one is actually the robot. And this is a sort of a reminder that at that time, you know, these computers, well, actually, 1947, but this is an advert from a bit later, actually, when their drums existed as workable things. But remember that the memories were tiny, but they were popularly described in the media as electronic brains. And there was lots of discussion about what electronic brains could do. Again, that's a subject of another talk. But this is their advert, is basically their drum is part of an electronic brain. What interests me about this is how big this robot is. How big is this robot? Because these are some drums. These are some ERA drums. Now, I haven't actually looked with a magnifying glass. I think it is actually possible that this is one of their smallest drums being held in the hands of the man who's in the middle of the picture. And I suppose it's remotely possible that you could fit that inside the head of a robot. But I don't think so, really. But that's advertising for you, isn't it? So these are some ERA drums from the late 40s and early 50s. Oops, sorry. Here's another one. This is MADIDA. This is Northrop Aircraft Corporation's magnetic drum digital differential analyzer. So this is a magnetic drum. It had 4 tracks, which stored a total of 22 18-bit registers. Per track, so that's 88 registers in total. But this was designed, the intention of this was that it would go in the Snark missile. So this was built to go as part of the guidance system of a missile. I have to say, the important word here is intended. And as far as I know, this was never actually actively used in a missile. I can't imagine how this could have worked. This is a mechanical system. It's a rotating drum. It's got heads that are held very close to the surface of the drum. How you could possibly imagine that you could run that in a missile that's bouncing around all over the place, I don't know. But this exists, and this is actually a photograph. It's held in the collection of the Computer History Museum in California. So it does actually exist as a thing. I'm not actually going to exhaust, so please don't tell me that I haven't mentioned whoever. I'm not exhaustively covering everybody, don't worry, but it's entertaining or interesting to look at what was happening in Harvard. So Harvard were looking at disk and drum memory systems from as early as beginning of 1947. By 1950, they built their Mark III calculator, which was an electronic drum system. So this was a beast. This was massive. So the memory of this thing was massive in those times. It held a total of 102 kilobits, I should say, not bytes. In order to do that, it had 8 magnetic drums, and each drum was 8 1/8 inch diameter and 40 inches long. 40 inches is about a meter, by the way, for anyone who can't do the conversion. And there were 8 of these. Each drum was 240 pounds weight. It's about 100 kilos. give or take. All driven by one 15-horsepower motor. So this is one of their schematic diagrams of their drum memory. This is plan view at the top and side view underneath. So you can see there are two blocks of there are 2 blocks of 4 drums connected in line. To the left of the drums, there's a gearbox, and to the left of that, there's the single motor that drives the lot. So each of the drums is 1 meter long, so the whole length of this is approximately 3 meters, and the whole thing probably weighs about 1,000 kilos, and that stores 100 kilobits. Here's a photo of it. So again, remember that each of these drums is actually 1 meter long if you want to scale it. So that's what, that's what you could do with drums at that time, if you really wanted to build a big one. If you want to, these 2 images, this one and the previous one, are actually we've got the report, the Harvard Computational Lab report. We've got the original of that, or one of the original copies of that, in the display case outside the lecture theatre if you want to have a look at that, and that's where these 2 come from. That's one of the holdings of the Manchester Library. Okay, so that's some examples of what was going on in the United States at the time. Back in England, I think it's fair to say that the first work on magnetic drums was done in Birkbeck College, London, by Andrew Booth. Andrew Booth worked in crystallography, and he built automated computers to do crystallographic calculations. And very early on, Booth recognized that storage was really the important problem that needed to be solved. And Booth, as with Williams, Booth toured the USA, initially in 1946, and later in 1947, he made a much longer visit to Princeton and stayed there for quite some time. And I think that was actually quite influential on Booth and on the work that he did. And while he was at Princeton, he discussed magnetic storage with Bigelow quite extensively, and particularly we know that he discussed single-turn heads and probably thin magnetic film drum coatings. So those ideas came to Booth primarily from his time in Princeton. Exactly who originated those ideas in discussions I really couldn't say. So Booth returned to the UK, and he built his ARC machine, or his automatic relay calculator, which was designed for crystallographic calculations. And he made a working magnetic drum store by November 1947, and he reported that by February 1948, he was storing 256 21-bit words on his magnetic drum store. And this is it. This is Booth's magnetic drum store. This is held in the Science Museum in London. It's part of their collection now. So this is a nickel-plated drum with a single head. And there's a fairly good, reasonable claim that this was at least the first working computer in the United Kingdom. I have to qualify that very quickly. Being from Manchester, I have to quickly say but. And the but is that it was an automatic relay calculator. And relay means he used electromagnetic relays, or electromechanical relays. So this was not a fully electronic computer. I don't think there was a single valve in it, as far as I know. I just checked there isn't one. No, there isn't one in the picture. But this was actually a working computer that worked during 1948, probably before the baby, as a complete computer. But again, as I say, electromechanical and not electronic. Okay. So what was happening in Manchester? So let's come back to Manchester. Manchester had established that they needed a secondary memory. They needed a big capacity memory to go with their CRTs. Some things that we do know. So where did the idea for a magnetic drum come from? Probably Williams got the idea of a magnetic drum from the States. But we do know that Williams actually met Booth in 1947. Booth came to Manchester and met Williams. And Kilburn actually went down to visit Booth in November 1947 before they started work on their drum store. And at the time that Kilburn went to see Booth, Booth actually gave Kilburn some single-turn magnetic heads to use in a drum store. So quite a lot of the ideas for the first drum actually, I think, came either from Booth or from the States or via Booth from the States. So, you know, there is no claim that Manchester did innovative work on magnetic drum stores, except for Manchester Code, which we will come to. We will come to. So just a quote to give you an example of the nature of the world at that time. This is a quote from Di Edwards, who was an MSc student at the time, who says that the drum was machined in the Department of Electrotechnics from a brass cloud chamber casting that came from the debris of the physics department. I'm assuming by that what he meant was stuff that had been discarded, unwanted old equipment in some old store somewhere. I don't think the physics department had been totally destroyed or anything like that. But that was the way that things worked, that they went around scavenging whatever they could from anywhere that they could turn into something. And that's how the first drum came about. They obviously needed more effort in this than they had. And so in the time-honored way of academics, what they did was recruit some students. And they recruited 2 students at the same time, Di Edwards, who worked on the transfer electronics between the cathode ray tube and the drum, and Tommy Thomas, who worked on the mechanics of the drum and the heads, and as it happened, on Manchester Code. Again, this is another quote which I rather like, which again describes the way in which all of this came about and how it was happening. This is a quote from Tommy Thomas, who worked on the drum, and he says, "The day when FC, Freddie Williams, having made his selection of nickel, looked out of the windows of the lab and spotted the motorcycle component electroplating shop across the road was magic. Off goes FC, clutching the body of the drum, and arranges within the week for the return of our plated surface, ready to start a series of developments." So yeah, it was machined out of an old cloud chamber casting and then plated in a motorcycle repair shop. There you go. This last bullet point is doing, in modern terminology, this last bullet point is doing what they would say is a lot of heavy lifting. The drum was then re-engineered by Ferranti. There was already collaboration between the university and Ferranti on engineering, properly engineering machines, you might say. The drum was re-engineered by Ferranti. So they had a drum. They got some heads, they got a drum. Magnetically, it was working. But there was a problem. So this is where we come to the new bit. They had got the idea of single-turn heads from, I think it originally came from Princeton via Booth. I should explain, a single-turn head is where you take one piece of wire and wrap it one time around a piece of magnetic material and use that to generate the magnetic field. Essentially, the more turns you put around a piece of magnetic material, the bigger the field you get. Or alternatively, you can have a very small number of turns and use a very big current to get the field. So they had single-turn heads, and that meant they needed a big current. And for the heads that they had, to generate the field they needed for the nickel drum, they needed 15 amps. And you can't get 15 amps out of a valve, or you couldn't at the time. So the valve electronics they were using wasn't sufficient, and they therefore needed to put a transformer between the electronics and the head. And the problem with that is that transformers will only pass through signals that are changing. So if you have a constant signal and you try and put it into a transformer, it doesn't come out the other side. So if you have a data stream which has a long series of zeros or ones, then it won't pass through the transformer, it won't get written. So they had a problem. And what they had to do was to try to find a way to keep the signal changing in cases where you had strings of ones and zeros. So Williams's solution was Manchester Code, or as they called it, phase modulation or phase encoding. So what you do in Manchester code is instead of recording data simply as a low level or a high level, the values 0 or 1 are stored as transitions instead. So a 0 is stored as a change from a low to a high state, and a 1 is stored as a change from a high to a low state. And that means that if you have a long series of zeros or ones, then you're introducing changes all of the time, and that will pass through the transformer. A slight technical problem is if you have lots of ones, you can't keep going high to low, and so in between you have to put a low to high transition, you have to introduce an extra one. But essentially every time, every bit of data, there is at least one transition, and in some cases two. So if this is the clock on the top, and this is the data, an example of some data underneath it with a string of ones and a string of zeros, then Manchester code is underneath. And basically what it's doing is it's merging the clock and the data to work out where transitions should appear in time in the final signal, and that's what gets written into the head. So it's actually quite a simple code. As codes go, this is trivially simple. But it's very useful and very effective. And the big advantage as far as Manchester at that time was concerned is there's no DC in this. There is 0 DC content in this code. It's also very, as I said, very simple to implement. And because it's simple, it's robust. Because there's a lot of clock information in there, it's also robust. In coding terms, what this actually means is we've taken these two signals, the clock and the data, and we've merged them together into one, and what gets written onto the disk is actually the combination of the clock and the data, and both things are there. And in storage terms and communication terms, that's very important. I'm not going to talk about that, but hopefully that will come through in the next couple of slides. So, this is the eventual memory of the Manchester Mark I computer. This is the original schematic from one of the first papers describing the overall memory architecture of the machine. As it evolved to a state where it had 4 storage tubes, 4 CRTs, each of which stored a page, so page 0, 1 to 3. And the electronic system potentially could have 2 drums. 2 drums, each of which could have 32 heads. In reality, what they actually built, I think, was a system which only ran with 1 drum, but had all of the heads on 1 drum. But it was originally designed for 2. So of the 2 students that were recruited, Tommy Thomas basically worked on this chunk, and Di Edwards worked on this part on the transfer electronics. So the 2 students between them basically built the first system, the memory system for the Manchester Mark I, and the first system that used Manchester code. But what I failed to mention on the previous slide is that the invention of Manchester code was actually Williams. It was not Thomas. So it was Williams who invented it, and then his students instantiated it in this. So one feature that I will mention about, and then I'll move on, about the Manchester Mark I is that the system clock was connected to both of the memory systems. So there was one system clock that connected to the CRTs and clocked all of the data within the CRTs, and also connected to the drums and synchronized the rotation of the drums and synchronized the data in the drums. So that meant that if you wanted to transfer data, everything was driven by the same clock, so you simply read from the drum and wrote it directly to the CRT. Modern storage systems do not do that, because, well, you can't. I'll leave that till later, till somebody else. So what that meant was that the embedded clock, which I described earlier that exists in Manchester code, which is one of its greatest advantages, in fact, wasn't used. The only reason they invented Manchester code was because it was DC-free. That made this system work. They never actually used the embedded clock in the system at all. It was incidental. Okay, practicality about how this thing worked. When this was first built, there wasn't room in the machine, in the room that housed the machine, there wasn't space to put the drum. So the drum was in a room upstairs directly above the main machine room, connected by wires. But it was also connected by an intercom because they hadn't developed the instruction set at that point. So what would happen would be the program would run to the point where the programmer knew that there would have to be a page transfer, and then the program would halt. And at that point, the operator, in this case, this is one of the famous photographs of Williams. Kilburn is, well, this is Kilburn's hand here. But this has been massively reproduced. But one of the interesting features of this is that right next to Williams's mouth, you can see this thing here on the console. This is the intercom. And that's the intercom for talking to whoever's operating the drum store, which is probably Thomas. So the program would halt. The operator at the console would speak into the intercom and say, please will you transfer track number 27 to CRT number 3. And Thomas would flick all the right switches and then press the button and that page would transfer. This was obviously automated as soon as they could, so they developed some what they call magnetic instructions so that you could write the instructions into the program and the program would run on its own. And thereafter, there is another very long story, which I won't start today, all about page transfers and where that eventually led to in computing. Okay, so here's a couple of pictures of Tommy Thomas and the wheel. This one is probably more reproduced than this one. I wanted to show this one because I think this is the only instance where I ever won a discussion with Simon Lavington about anything, which was, I told him that I believed that there were 2 drums, and he was absolutely adamant that there was only ever one, and that the Manchester Mark I only ever used 1 drum. And if you look closely there, so you can see 1 drum, right in the middle of that photo, you can see 1 drum. If you look to the right of it, hidden away underneath a shelf, you can just see the edge of a 2nd drum. So there were 2 drums, and the system was designed so that you could run from 2 drums. In the end, they found it easier to put all of the heads onto 1 drum, and generally didn't use it. Anyway, so this is Tommy Thomas, who built the system. Very quick postscript about the drum store. In the days of, as in research nowadays, once a piece of research equipment has ended its life, it just gets dismantled and chucked away. And that's pretty much true of everything that happened at the time of the Mark I and the Baby. The drum store, though, went on to have another life. One of the future projects that happened in the department was Dick Grimsdale built the first transistor computer. And he was so determined that there wouldn't be any valves in it that for the memory he used the magnetic drum store from the Manchester Mark I because there were no electronic valves in it. So this was entirely transistorized as a computer. So it went on to have another life afterwards. I just mentioned afterwards when we finish there are some of these things on display. We're going to have the reception up in the 1st floor just above this level, at the level of the back of the lecture theatre. If you walk around the courtyard from there, you'll find some artifacts on display, and amongst them we've got one of the heads from the Manchester Mark I drum. So that is probably one of the first head that wrote Manchester code onto a practical device. And we have a Mark I drum from the Ferranti Mark I. And in the case that's at this level, just outside the lecture theatre, we've also got Tommy Thomas's MSc dissertation, of which one of his relatives is here with a bound copy, which I didn't know existed, up there. We've got the unbound copy, which is in the university archives, and also the Manchester Mark I handbook, which was written by Di Edwards. So the 2 students who worked on the 2 aspects of Manchester code, we've got their work describing the system, so you can see those in the display case out there. And I will finish just with a brief thanks to, well, thank you to many, many, many people, but particularly John Ryland's University Library, who've been phenomenal in me putting together the research for this. The University of Manchester Archive, which is part of Special Collections, tremendously helpful, and they've also released the documents for the display. But also Interlibrary Loans, who are tremendous at finding obscure documents that you give them very partial references for, and they will sort of magic them out of nowhere. And I was most surprised when they actually produced a confidential US Navy report for me. So great thanks to the Navy, to the library, not the Navy. Navy, okay. Okay, so I think that's me.
Jim, thank you for a great talk and demonstrating the history and the development of technology in the sort of late 1940s and how it impacts us still today. I don't think this is a seminar where we're expecting questions, but I don't know if, Jim, if you have any history questions. Okay, we have a question. Tim.
The obvious one, Jim, why did they stick with this? What constrained them to sticking with a single turn?
So the question was, what constrained them to stick with a single turn? I think it was just what they got.
They couldn't afford more wire?
They could, well, they did go on to make their own heads. They could have made heads with more turns. As to why they carried on with what they got, I guess it was working, and so why would you change it? Because they'd actually built a working system. So I don't know. I didn't look for the answer to that, so I haven't found it.
All right. Anybody else on a history question that Jim? Sorry. Yes. Apologies.
Yeah, just a very quick comment. You talked about the first transistorized
Yes.
version. I worked on AnyDeck in the 50s.
Yes.
Because they were discrete
Yes.
transistors, every one was individually tested.
Yeah.
That was the state of transistor technology.
Yes. Yeah, this was very, very early in transistor technology, and I think to some extent the design was severely constrained by what transistors they could get as well, and as you say, they had to characterize each one. So yeah, non-trivial.
Okay. Any final question which I'm not going to miss? Don't think so. Let's thank Jim again for a really excellent talk. Okay, so it's my pleasure to introduce the second technical talk, and this is going to be given by Kees Imack on the consequence of Manchester Code for data storage.
Thank you.
Kees,
thank you.
Please.
I also stand over there. Oh, good afternoon. For me, it's a pleasure to stand here on sacred ground where all these famous people working, like Kilburn, but also, of course, Alan Turing. He gave the name to my company, Turing Machines. So for me, a very nice place to be here. And why am I here? Well, actually, I was invited by the IEEE to look at the nomination, to review the nomination made by Jim. I didn't know Jim at this time, but of course, IEEE doesn't accept any nomination at all. So the other people, independent people like myself, had to look, and I found it great. It was a great invention and a great nomination as well. And then a year or so ago, Jim invited me to come here and tell a little bit about the Manchester Code in data storage. And just to introduce myself, I've been working essentially all my life in data storage, first starting in optical recording, like the CDs, compact disc and DVDs, and later I worked on magnetic data storage on tape, like the digital compact cassette and digital video recording. Probably you all use that kind of consumer electronics products. And I designed all the codes for all those systems. So I know a little bit about constrained codes. And of course I knew and I know about the Manchester Code. And Jim already told why a Manchester Code actually is being used, because in many modern consumer electronics products, many types of codes are being used. For example, a source code that compresses, for example, the high bit rates that you got for video, digital video, into small pieces, or error correcting codes that corrects errors that are made in tapes or on disk. But also you have this kind of Manchester code that are usually called constraint code. They follow specific constraints that the physics of the channel impose on the data stream. And Jim already said, for example, that you need transitions from 1 to 0 or from 0 to 1, because otherwise you cannot use it in combination with magnetic tape or magnetic transformers, because of the one, well, anyway. So let us take an academic look at what these constraints can be in physics, okay? And these constraint codes, they enforce specific constraints on the digital stream that are recorded to enhance the system performance. They do not correct errors. They are not error-correcting codes. They circumvent the occurrence of errors, okay? That's why these kind of constraint codes are used. And I will show you, they make communications possible. They make data storage possible. If you don't have these rapid transitions between ones and zeros, there is no storage possible, essentially. That's also what my predecessor said. And to limit interference and enabling clock synchronization, already Jim mentioned that. To shape the signal spectrum, so DC-free code is essentially shaping the spectrum of the recorded signal, and so on. The last sentence makes it very clear, I think. Constraint code is an existential importance in most digital storage systems. And the next sheet is a little bit tricky because, well, I will explain you why it's tricky, because I think it will explain in one sheet why it is existential. Because most communication people, they focus on the average performance of a system. But a constraint code focuses on the worst case performance of a system. If you don't have a transition between 1 and zeros, or if you don't have a limited run length, where a run length is defined as the number of ones, consecutive ones, or consecutive zeros that you have. If you don't limit those, you run out, well, essentially at a certain time you run out of the system technology. For example, the average maximum run length between ones and zeros is 2. But worst case, it is infinite, okay? So, well, these kind of constraint codes say, okay, we will constrain the maximum run length, for example, to 10 or 7 or 8, or at least a limit. So you need that specifically in very early transmission systems. And this is a very early constraint code. This is very tricky, because maybe you will remember that in Manchester University, they use smoke signals, okay? So that's why I find it very tricky. But anyway, if, for example, a smoke is a 1 and a non-smoke is a 0, then essentially, if you have too many non-smokes, your blanket or your carpet will burn, and there is no transmitter anymore. Okay, now you probably understand why maximum run lengths in binary coding are very important. Yes? And that has been my career for almost 40 years, to limit maximum run lengths and to make spectra possible. Also, for a Dutch engineer who likes street organs, also there you will find maximum run lengths. Here you see the music books in street organs. And every run length is just a tone of one of the pipes, okay? So if you have 10 minutes of just one note, the book will be split in 2 or in 3, whatever. So also here, the maximum run length of one tone is limited, okay? So forget about the smoke signals at Manchester University, because, well, I don't want to receive any mad emails from the Vice Chancellor, of course. The applications of these codes, constraint codes, are specifically in solid-state memories, flash, magnetic disk and tape drives, and optical disk drives. All optical disk drives use it. And later we will show that also on DNA-based data storage, that will be in the offing. And this is the Manchester Code. Manchester Code is very simple, and it just depends on how you look at it. In normal lectures, I will explain it in maybe 2 minutes, but now we have 25 or 20 minutes to explain the Manchester Code. And you can look at it as just a 1, and you add just the inverse of the source bits that you got. So if you have a 0, you will add a 1. If you have a 1, then okay. And that gives you the transitions that are possible. And also, it also limits the maximum run lengths of 1s and 0s, and also has an advantage in spectral content, so that you can use it with systems that have a transformer. The only disadvantage, Jim didn't mention the disadvantage of the code, is that this code has an efficiency of 50%, because 1 bit, source bit, is replaced by 2. Yes, and that's called an efficiency of 50%. Coding people like myself call it a rate. The code rate is 50%. And so essentially you lose 50% of your density, bit density, or your communication speed, or whatever you are talking about. I talk about data storage. There you talk about density, how many bits you can have in a millimeter, or in a micron, or in a nanometer. So, okay. This is it. This is the whole invention. You could see, and maybe Peter will explain it, but you can also see the Manchester Code as a choice of a waveform. You can actually represent one by just a level of 1 volt or 1 ampere, but you can also represent it by 1001. Anyway, the applications are very wide, already starting in 1964. This is the 9-track magnetic tape. It has a density of 1600 bits per inch, and the total capacity of this tape was around 170 megabytes, not gigabyte. Huh? We're talking about megabytes, because in your PC computers we talk about gigabytes normally. These things have been, well, you could see them in all movies and TV series. If you look at a computer, the mainframe computer, you always saw these running magnetic tape drives, and that's all you could see. And oh, he was thinking, and the computer was thinking. Oh, yeah, you saw the tape drives running. And it used the Manchester Code. I didn't know that actually, but anyway, I looked it up. These are the IBM drives that were introduced in 1964. Fantastic machines, great. This is probably a thing that you know from the 80s, the 1980s. This was the Atari floppy disk with the 5 1/4, so the large one, the large floppy disk. And it could store 80 kilobyte, and it also uses the Manchester Code. And it's a fantastic product. It was first used in the PCs, probably you know it all. And then later we get the smaller floppies, but I haven't the slightest idea what kind of code they're using over there. But anyway, this is a fantastic machine. I wished I was older and I could work with the IBM people working on this kind of machines. It's fantastic. It's absolutely great. It was the very first disk drive that was introduced, of course, again by IBM in the United States. In '56, only 5 years after the invention of the biphase code here in Manchester. I call it, the Manchester Code. Normally I call it the biphase code, but anyway, but it's the same name, of different name for the same product. The Manchester Code, and well, it's a huge machine like this, and the capacity is 5 megabytes. I'm not sure about the price, but probably, I guess it will cost you $100,000 or so. In the 50s, that was a huge amount of money. Also using the Manchester Code. Fantastic product, absolutely top of the bill. I just show you, well, now we have to become more academic and explain you what the run length limited codes are. So there are codes, not like the Manchester Code, but other codes that actually guarantee that there is a minimum run length and a maximum run length. We can explain the maximum run length because, well, you want to limit the distance between the transitions of a binary signal. But also, specifically for magnetic disk drives and in optical disk drives, there are also a minimum run length. So you want to have at least 2 or 3 bits, consecutive bits of the same polarity. You like that because that the longer the minimum run length is, the smaller the maximum frequency in your signal. Okay, so you actually are shaping also the frequency response. And essentially, all magnetic disk drives in the 70s that were very important by IBM use run length limited codes, and also all optical recorders like the CD, DVD, and Blu-ray, they all use run length limited codes that also have a spectral shaping characteristic. They also limit the power or make it DC-free. They also limit the power at low frequency, not because of the transformers, because optics does not use induction with one term. But for optical recording, there is a servo system that's following the track on this optical disc. And if there are low frequency terms in the recorded signal, then the servo signal cannot easily follow the track. So there's a completely different reason than why Tom Thomas invented the Manchester code, but still in optical recording we have DC-free signals and also run length limited signals. So the combination of both. It's now very mature, and also optical recording is, well, essentially obsolete. Magnetic recording is still there, I'm sure. So this is the history of the run length limited codes in the optical disk drive by IBM. Again, IBM, the 3370, using a 2.7 code, where 2 stands for the guaranteed minimum run length, number of zeros between ones, and the 7, the maximum number of zeros between ones, and the ones indicate the transitions. So that was 1979, and they ran for at least 20 years, these machines, and so they were used up till 2000 or so. And yes, this is the disk drive that was used by IBM in the big mainframe computers, the 360s and 370s. And the capacity is 1 gigabyte, and it is the size of around a refrigerator. Okay, costs you $100,000, which is a lot of money, but most of the insurance companies bought maybe 200 or 300 or 1,000 of these pieces, because that's, for insurance company, that's the only thing they need actually, is memory, and it's only 1 gigabyte. Not terabyte, only 1 gigabyte. The weight is 30 kilogram, and they're using a run length limited code. And there is no spectral shaping in it, it's just a conventional run length limited code. A beautiful machine, absolutely top. The pits, so you have pits in the plastic of an optical disc, okay? And the pits have a minimum length of around 833 nanometers and a maximum size of around 300 microns. So that is 11 clock units for the maximum and 3 units for the minimum run length. And and that's essentially everything that you will find on an optical disc, on a DVD. If you have a good microscope, you could look at and you could see the discs and the pits and the lens in between. They also have this kind of length, okay? So that is 9 lengths, yes, or something. Anyway. These are the products in optical recording, and I was spending my youth designing codes for these kind of things. But anyway, it was very, very good time doing it. And This is new. So this is what we've done, also what we did here in Manchester Code, but also what we did for optical recording. This is new, okay? So also in DNA-based storage, we can store information. So DNA, oh my God, you always get questioned, but all the DNA, your material, and it carries the genes of all the information, how you could build human beings or everything. This is different. It's DNA, sure. But you can go to a factory with a memory device and you can say, can you make 1 million of molecules with DNA? And the molecules are just probably nucleotides that have four possible variations. That's called A, C, G, and T. And you can actually design, and well, factories can actually come up with these molecules. And the molecules are in a container, small container, or a large container, usually very small, because it is very expensive to fabricate, to manufacture these DNA molecules. It costs you probably $1 million for a megabyte. It's a lot of money, and there are maybe better ways to spend your money, but anyway, it's... and now you put all the molecules in a vacuum, and then later, when you need the information, you can actually restore the information if you need it. This is now in the offing. Well, essentially, 10 years ago, the very first experiments using data storage has been performed in the United States, of course. And they stored some movies in DNA and could restore it later. And the predictions is, and this is that you can store the whole internet in, let's say, a pint of beer. Well, of course, first remove the beer and then put all the DNA in it. And it's enormous. It's enormous, yes. So the prediction is that it is, well, that it can store a huge amount of data. But the question that I expect and that I already answer is, what is the disadvantage? Because, well, the disadvantage of having DNA data storage is that all these molecules will not remain in the same place. They are just like tea leaves in tea, they floating around. So you have your information floating in this container, but you don't know where it is. But I'm sure it is, you know? I'm sure that you know. So this is difficult, because if you want to restore the data, you have to recover all data in the container, because, well, of course, I'm a worst case person, so I know that you have first to look at everything, and then you will find your own information that you need. But anyway, lots of people, coding people like myself, who have nothing else to do because optical recording is out, so you have to do something else, are doing this, and it is great. It's absolutely great, because also here, we expect to use constrained codes, just like 70 years ago, Tom Thomas starting with constrained codes for use in the data drums, and now, 70 years later, people like myself and my colleagues are contemplating using these kind of constraint codes for use in DNA-based storage. And I think, oh yeah, also in the digital compact cassette that you could buy maybe 30 years ago, was a nice product. They also use tape and they use digital audio, and they also use DC-free codes, but they don't have an efficiency of 50%, but these kind of codes have an efficiency of 80%. So in the same kind of, well, the length of tape, you can store more music than in that. And okay, that's the next one. So thank you very much for your attention, and that's it.
Thank you very much for that. It's really interesting to hear from one of the experts in data storage from the optical fields for that. I should point out that Keys has 1,100 patents in your,
That's
to your
what
name.
they say on Wikipedia. Yes, so it must be right. So,
so that's more than most of us.
But it only tells you a thing about the deep pockets of my employer, not about the...
Yeah, no, it's really interesting to see, you know, coming from a data storage background myself, to see some of these things. Yeah. Now, are there any questions for Keys that we would?
Yes.
Ron.
Are the tracks on an optical disc concentric or spiral?
They are spiral. Yes, that's a good, yes. And magnetic discs, they usually are circles, huh? Real circles, and here they are. And that makes it also very important that you have a track, because if you have no series of pits and lands, there is no track at all. So if you miss, say, 1,000 or 10,000 of zeros, there is no track at all. There is just empty space, because the ones and zeros are the track. So that's why this worst-case design in optical recording is even more important than in magnetic disk drives, because there the track is always there. And the mechanics knows where the track is, because but in optical recording you don't know where it is. You just have to search for it, and it's very interesting. As an engineer, optical recording is much more interesting than magnetic.
Controversial.
I knew he is a data. I take great risks, also with the smoke signals, but also with the... Yes, please.
With DNA storage, will you have problems with random access? Or is it... Yeah?
Impossible.
Sorry?
Impossible. Random access is impossible. Yeah, and if you want to access specific information, it's not possible. You have to read all information and try to find the information. Yes. Well, of course, there are some people working and say, okay, let's just glue DNA material on a very thin piece of paper or a piece of material. So just like in disks, because that's the advantage of tape and disks, specifically disks, because you have a list of contents or whatever, and you know where all the bits and the bytes are. So you just have to access it, and the user itself probably doesn't even know where the information is. The computer data, the disk operating system knows where everything is. So well, but in DNA-based storage, it's impossible. Just I explained, it's like tea leaves floating around, and on one of those leaves, the data is stored.
So what would you use it for?
Well, yes, good question. Very good question. Where do you use it for? Well, sometimes, and you can actually find archives of the, for example, of the internet. So you can just store the internet and have a picture of the internet at a certain moment, and then you can maybe 100 years later or 1,000 years later, if you have the right equipment, of course, then you can restore the information. But anyway, one of the advantages that the DNA people say of DNA is that it has that you can store the information for a very long time, because, well, you can now find elephants or whatever, or that lived 100,000 years ago, and you can actually restore the DNA. I give you a good question, but then you ask them, well, that is for natural DNA, but what about synthesized DNA? Oh my God, then you don't get any answer. So, well, it's an interesting topic. It's for the academic world, it's very important to do interesting things. And this is very interesting. Just like Thomas, who did the experiments in 1949 on the drum. He didn't know that it was becoming very important later, but he did his master's thesis on the thing. And, well, we don't know what will happen, but we need people who do new things and can be enthusiastically working around it. So, anyway.
Thank you for that. If you want to see the master thesis, I think Jim has got it out and it's on display in the cabinet just where the desk was with the tickets. So the actual physical document that was written is there today to prove that. So let's thank Keith again for an excellent talk. Okay. Our final technical talk is another University of Manchester speaker, Professor Peter R. Green, who is Deputy Dean of the Faculty, yes, something like that, of Engineering. But much more importantly, for the purposes of this meeting, he is Professor of Wireless Communications in our Department of Electrical Engineering. Peter.
Thank you very much. Lovely to meet you all this afternoon. Not quite sure how a professor of wireless communications follows smoke signals. It's a nice lead-in, Reese. And by the way, you can tell the Vice-Chancellor, because according to the health and safety reports, one department still does use smoke signals, by the way. Not that I'm calling out the chemist, you understand. Yes. Oh, they're not limited at all. So I'm the imposter here in the sense that I can't prove to you where the communications community, let's use the word plagiarized, and pulled biphase or Manchester code across into our domain. But what I do want to show you this afternoon is just how prevalent it is. So if we're looking for evidence of widespread and impactful use, that's hopefully what I'll be showing you. So I want to spend a little bit of time, first of all, talking about wired communication. You'll see why the link works. Talk about Manchester code, and then literally walk you through some applications largely in the wireless domain, and then just reflect because, and I was so grateful to Jim and the IEEE for asking me to do this because it's forced me to review a sort of 35 years in this space and suddenly realize how many projects, how many work I've done use Manchester code. And I feel slightly awkward, a bit embarrassed that I've never sort of mentally sort of called that out. So, the starting point. Let's go wired to start with. Forget wireless for a moment. Basically, back in the 60s, 70s, we were doing a lot of work with synchronous serial. So this is where you have two systems interconnected, and a modern example would be things like SPI bus, I2C doing chip interconnect, where you have a clock signal and you have a data signal. And your clock signal tells you, in effect, when to sample the data signal, and therefore your data is recovered. And it was seen to be the way, and some very large telecoms networks would dedicate two wires, one to clock and one to data. And then, as I say, you can use the one signal to sample the other. This is still in use, as a largely to do with chip-to-chip interconnect. Obviously, that becomes problematic, A, if you're doing long distances, B, if you are starting to get precious about the number of signals. So no surprises, we then went across to asynchronous systems. So this is where I do no longer have a clock signal between my transmitter and my receiver. Now, obviously, you'll see where this links then to wireless. So what's my problem here? My problem is, yes, I can connect two devices. Yes, as you can see in the top part of the right-hand diagram, I can time out a set of bits. I can use a master clock in my transmitter to set that timing. But how on earth do I recover that timing at the receiver? And the classical way was, well, why don't you have something that signals the start of transmission, a start bit? When you see that edge of the start bit, a local clock, and let's think carefully, it's not the same as the master clock, hopefully it is similar, can start timing into the middle of all the bit values, which is the optimal point to sample them usually, and then you recover your data. This system works. It's been out there for years. A lot of what people call RS-232 in a very loose sense was actually transmitting data of this form. But where does it go wrong is when you start to have very long runs of bits. Great for 8 bits, but let's imagine it's 800 bits or 8,000 bits or more. the disparity between your transmit clock and your receive clock become problematic. And you get this clock drift. And so the deeper you go in time, the less chance you have of hitting the middle of the bit cell. So technique works well, just transmitting bytes, but is weak when it comes to actually working with long, continual streams of bits. And so with that in mind, there are limits on the frequency you can use, the bit rate you can use, etc. And so we move across, and this picks up from where Reese was talking about line coding. So here was the concept. I've got a transmitter and a receiver. They are interconnected, let's do it really simply, by a wire or a fiber. How would you like to encode your bit pattern? And at the top, labeled NRZL, is the most primitive form, which is, in a sense, what we treat as raw data. Logical ones, logical zeros, just two separate voltage levels. Now, as the two previous speakers have said, the problem with that very simplistic way of transmitting bits onto a wire or a fiber is, if you have very long runs of zeros or ones, what is your concept of clocking? How do you recover the original clock which was used to synchronize the data transmission? Now, you can play lots of different flavors on line coding, and there are literally 40, 50 line codes that people have played with over the years, of which Manchester code is one. And what they're all trying to do, to some extent, is embed, as Jim said, clocking information into what you transmit so you can recover the original data. And they do it to varying extents and complexities. But this concept of just transmitting the raw signal, NRZL, is hugely problematic. It implies DC components. So if you look at the spectrum of that signal at the top, for arbitrary signals, you need to be able to transmit DC. And as you're going to see in a minute, that is actually problematic for a number of reasons. So, I think we've all probably used this diagram this afternoon. So Manchester code, in a sense, is addressing the very problem the previous speakers have referred to. How do you embed in the signal you transmit clocking information? And Manchester code does it with great elegance. It introduces transitions, as Reese was said, with sufficient periodicity that you can recover the clock. Now, this could be a phase lock loop approach, although actually in a lot of embedded systems, it's even now done in software. But you only have to look at the data signal and one of the two Manchester encoded signals to see there should be a difference in spectrum. You just look at the Manchester signal, you see far more rapid transitions. And if you take the case of transmitting all ones or all zeros, you will have twice the frequency you would ever have in the original signal. And that says, and this is one of its downsides, it's going to take twice the bandwidth. And if bandwidth is precious to you, and it is in my world of wireless, that could be seen as the biggest and single biggest negative. Why the two codings? Well, as with all line coding, you can invent twists on any rule. So in the original G. Thomas coding, you can decide that a 0 will be a transition of a 0 to 1, a rising edge. Nothing says it can't be a falling edge. And it turns out that one of the IEEE standards flips it round and uses it as a falling edge. It doesn't matter so long as you know which one you're using. And you can have some real fun if you invert it. Now, several speakers have spoken about the properties. Here's what's important to me as a wireless comms person. It must be self-clocking. It's a waste of time otherwise. I need a signal that when I receive it, I can extract the clock to be able to resample the data. I definitely want no DC component or a very low DC component. Now, I'm going to show you an example where this is absolutely vital. Manchester does that. I'd love to have high bandwidth efficiency. As we said, it's 50%. It's low, it's not great, but that may be a useful sacrifice that I'm prepared to make. I need it to be robust, and I'm going to show you a couple of applications where that robustness, the ability to recover the clock to retime my data, is worth the bandwidth. And I know we said about error detection. It is not the purpose of line coding to implement error detection. There's other methods to do that. But Manchester does let you do some really primitive but very effective error detection. I know where clock edges should be. So if they're not there, I can know something's wrong. If I detect an extra clock edge, I know something's wrong. So there's actually some quite nice things I can do that come for free. And it really is the inspiration for modern codes like 8B, 10B. So 8B, 10B is simply where you take 8 bits and you encode them effectively into 10. It comes back to the efficiency that Rhys was talking about. So there are some very modern approaches to this, but I would actually say they all inherit the concept of Manchester code. So a quick run through some applications. Now, 802.3, an IEEE standard, absolutely in its early days and early incarnations, was based upon Manchester code. So for those who can cast their memory back, 10 base 5, which is the picture on the left, this was when we used to have a lovely thick Ethernet cable that ran through all of the office and lab space. And where you wanted a connection, you had something called a vampire clamp, which you clamp on the cable, and it truly does, sticks a spike right through the coax cable to the inner core. Obviously, you've got to get it right. You can't make it look like a colander after you finish with it. But literally, you could have 5,000 meters of this and just pick the points at which you put your network. We then moved on to 10 base 2. And the picture in the middle perhaps doesn't scream 10 base 2. That is my abiding memory of the first network I used at the university. So in every office, you would find a wonderful little BNC connector somewhere hidden down on the floor, which was your connection to the computer. And depending how mischievous you wanted to be, if you disconnect that at the end of the day, you could effectively kill the whole segment. And so if ever the network went down, you had to walk through every office. And by the way, it was the first excuse I ever had to get a master key in this university, was to walk through every office checking all the BNC connectors were back together. And then a more modern 10 base T. So the very early twisted pair network connections, again, it was using Manchester code to actually encode the data bits. Now, this is going to be one of the first applications where this lack of a DC component is going to be vital. So Profibus is, well, I'd probably say it is the dominant bus used in the process control industry. So we're into tens of millions of deployments of these buses. What you're seeing on the left there is a set of Profibus controlled water valves, in effect. That's a very big sewage treatment plant, and those are the water flush valves, and they're all controlled electronically on this bus. The bus uses biphase or Manchester coding for all its data streams. It gives great robustness. But here's the critical thing. If you think of a lot of the process industry, it could be handling flammables. Think of things like where we go from oil to gasoline process plants, any form of a refinery, any form of liquid petroleum gas. Then critical or intrinsic safety is really important. So what you don't want is a sensor sitting on the end of a long length of wire where if it fails, the current could go so high the sensor or the cable catches fire and ignites. So now you want a system whereby you can control the power. And so what Profibus does is say, right, I'll give you a single transmission path, twisted pair. I will send the power down those twisted pairs, but I can control it, so I can monitor the current flow. So if it starts to get excessive, I will limit it. I won't allow a fire. But now I want to impress on top of that DC current the data. And suddenly this is where things like Manchester code not having a DC component is perfect. It doesn't need the DC, so you can join the two together and effectively be transmitting data on a twisted pair that also has controlled power. And it's actually called Manchester coded bus powered. So they've even kindly inherited the name for us, which is rather nice. People have mentioned infrared remote controls. Now, if you want to go for absolute, you win out, you get the IEEE prize for maxing out, try this one. I think last year, 300 million smart TVs were manufactured. Now, they're not being stored anywhere, so let's assume they're in people's homes. That is at least 300 million remote controls of some form. The vast majority of those are still infrared, not wireless. And if you actually look at the Philips RC5 and RC6 protocols, they use bursts of 36 kilohertz. Now, why are they bursting infrared? Well, the problem is, in every setting like this, there will be natural infrared from other sources like lights or sunlight or whatever. So to distinguish the signal from the background, they actually use a 36 kilohertz as a modulating frequency. But the actual data is Manchester coded on that. So we're using Manchester code to do the bit transitions, and that then fires the burst. So you can see the two data bits there, Manchester coded and as bursts of the infrared carrier. So if you want to look for reach of a technology, I'd love to claim a much higher, much more impressive technology, but remote controls are the things that do it. Now, another area, and this is, again, thanks to Jim, took my memory back. So before I joined the university, I worked in aerospace, and I came across this Mill Standard 1553 bus. Now, in the day I was working in aerospace, we were using it on military aircraft, as it happens. But actually now, it is widely used on most forms of both military and civilian spacecraft. I mean, there's ISIS, the International Space Station, which uses it for a lot of its data transmit around the actual space station itself. And there's one of the Galileo space probe also uses it. So why are we using it there? And one of the attributes of 1553 is it has an extremely low error rate. So you're talking about, I'm going to use their language, 1 word in 10 million words is corrupted and unrecoverable. Now, that may seem to you to still be quite a high number, but actually that is reliable by most network standards. So that's why you find them used in space. And then obviously you need radiation, hard electronics to do it. The other thing that's nice is this. If you want a communication data bus wired that is reliable, one of your biggest failure modes is one of your end nodes, receivers, fails catastrophically, often a power supply failure. If that failure drags the communication wires down or takes them up to higher voltage, you block the bus for every other device on it. So one of the problems when you try and build high reliability networks is how do you cater for end node failure without taking out the whole bus? And one of the tricks we often use is, first of all, redundancy. So 1553 has up to, but now higher, 3 redundant buses, so you get reliability through that. But the other trick is this. You want to isolate electrically the node and the bus. And if you think of the failure mode, a transformer is very convenient. You heard Jim talk about this earlier. So this time we use a transformer to our advantage that it doesn't allow DC to pass. So the power supply failure in the end node doesn't take the bus down. It doesn't stop other failure modes, but it removes the most common one. Now, for a transformer to work, as Jim said, I need a coding system that has no DC component and therefore will pass through the transformer because it's AC. And again, biphase or Manchester code ticks the box there. Now, I don't know about you, but during the pandemic, I strangely found that I'd been taught how to give away money more easily. I don't know, I was trying to think back. You take your credit card out and you tapped it on a machine. What was the original limit? Was it, I think in the UK, was it £20? I forget what it was. And it just slowly during the pandemic used as an excuse. I think I can now tap away £100 and it's just effortless and the money just flows out the account. Now, what is actually happening there? The first thing is obviously the credit card is not powered. There's no embedded storage device in it as a battery. So where does it get its power from? So basically what happens is your reader, which could be your phone, or is typically a card reader in a shop, generates an electromagnetic field. It's the magnetic field that's interesting here. So that magnetic field couples through two coils, one in the reader, one in the card, so it's like a transformer with air in the gap. And that is how the actual NFC tag, the near field comms tag, gets its power source. And at the top, you can see a typical way the data is modulated out to the card. Now here, the modulation, it's not Manchester, but it's interesting is, we mustn't have too many zeros in that, because effectively, I'm trying to transmit power to the tag. So they have to think about that. But it's when the card wants to transmit back to the reader, how does it do it? And one of the techniques, and there's many, is it's called load modulation. So what the card does is, it takes its antenna and periodically, it's almost like it shorts it out with a resistor. So it tries to present a way of absorbing power, hence load, and it modulates it in time. And one of the most dominant methods, again, uses Manchester encoding for the data transmission from the card back to the reader. So I'm hoping, building up a picture with you now, that this code is absolutely prevalent. It's actually hard to think of a domain or an area that has not benefited from Manchester coding. And again, why have they done it here? They want a really simple, robust way of being able to get the timing from the card across to the reader. Now, I think everyone in this room gets why that's important. And I have to not smile too much when you get PhD students who run simulations of communication systems, and they present me with this beautiful timing where everything just works. There's no clock slippage, there's no jitter, there's no nothing. Because what they haven't thought is that in one program simulating the transmitter and the receiver, it's like there's a hidden wire that joins the two together, and they just go, oh, there's no problem with timing. It's only when you force them to say, okay, put that one on that computer, that one on that one, now give it a go, that they start to realize this problem is everywhere and it needs to be solved. Now, another question that often comes up, and I use the word near field here because that's the name of the technology, is students often say as well is, I'll see them test a wireless comm system and the two antennas will be like that, okay? And you say, okay, let's talk about the idea of near field and far field with electromagnetic fields. And as a rule of thumb, you normally say you need to be at least one wavelength of the frequency you're using apart in order to move from the near field to the far field. So what's the difference? In the near field, the electric and magnetic fields are not propagating as a plane wave. They are very complex couplings, and they go through abrupt changes in field strength with distance. And if you put two antennas like that, you could achieve no communication or wonderful communication, but it's almost meaningless. Once you get one wavelength and bigger, you start to get the wave propagate as the classical 90 degrees, E field, M field, propagation direction. And that's what we're all used to. But I did, again, thanks to Jim, I was trying to think of, I've just done near field. What is far field? Well, you've heard the example earlier. If you want far field, think Voyager. You know, I think 2.58 billion kilometers is far field. I think I'm fairly safe that I can say by that point it is, it's a plane wave by then, I think. We're fairly safe on that. But here's a good example. And there's a lot buried in this. You could do a whole wonderful talk, actually, about Voyager. And we had a lovely conversation at dinner last night where I think one of the challenges for the current generations is it's all too easy. You take out your mobile phone. You can just dial someone. And 2 years ago, back where I live in Gloucester, we actually had a sunny day in Britain. We do, Reese. You asked me the other night. We do have sunny days. It topped out at about 27 degrees. And the mobile base station in the village burnt out the power supplies. So gone, no mobile coverage. Two things I spotted was, first of all, a load of young people walking around as if they'd lost all form of control, because their personal geo-navigation was shot to pieces. And then there was an interesting one. There were two of them standing literally that sort of distance, and they wondered why the one phone couldn't call the other. And I knew one of them is the son of a friend. And I said, what do you think happens when you make a call? And I'd never thought of this. What they, of course, thought was they thought in the terms of a walkie-talkie. And I said, but I know your uncle is currently in Switzerland. I said, what do you think happens when you call him? And you just watched the penny drop as they start. And I think one of the challenges for us in our domain, and I'll talk a little bit about the history in a moment, is that what we look at and think is outstanding, amazing, they don't understand because they're so used to communication being easy, storage being easy, and they just take it all for granted. We've got a job of education to do. So the uplink to Voyager, it's about 2.1 gigahertz, 16 bits per second, okay? Now this is a vital link. This is our only means to send a command. That command could be to, as we had to do once, to switch in the second receiver. I think one of the receivers failed. This could be the command to fire the hydrazine-powered rockets, to reposition it. It's absolutely vital link, and that is Manchester coded. And that is the main uplink that we use to Voyager. And so, and again, from a point of view of reliability, would I trade 50% bandwidth? Yes, I would. There's communication scenarios where you go, yeah, it's worth the call for that. The other thing, which again, you could say this to students, they have no idea of the numbers. That poor little spacecraft has got 22 watts now available for its transmitter back to us. And when you work out the power that is incident on the Earth from it, and you look at that number, 10 to the minus 20, this is why no single telescope now really can do the communications. We're having to use the phased array techniques of multiple telescopes across the world. But I'd love a student once to just sit back and watch their eyes open and actually realize how impressive that is. And I think that's, to say, one of our challenges going forward. I wanted to end with just 3 sort of personal reflections on where I have shamelessly used Manchester code, but haven't really given it enough thought when doing it. The first one is putting wireless sensors into gas turbine engines. So this is where you're trying to put a sensor between the inner case and the outer shell of an engine. And because there are no protocols for doing that, there are no techniques for doing that, we did it all with software-defined radio, but we had to build the signal from the ground up. And that was, Manchester code was the perfect way of me getting my data timing. The middle picture, and you can't see it close enough, but I'm the idiot at the back, trudging through the snow there, was where you're trying to put remote sensing, where you truly have no guaranteed power source. We were transmitting the signal purely opportunistically. I've got enough solar energy, I've got enough wind energy, and we bounce it off the ionosphere above the Earth because there is no infrastructure where these are going. And suddenly then, I only get to transmit once because I've only got enough power. I want to transmit it and modulate it so I've got my best chance of recovery. Hence, I went back to biphase coding, Manchester coding for it. And the last one, you may not recognise that. That's a picture of the Sellafield site in Cumbria, Britain's biggest nuclear and legacy site. We are desperately trying to deal with the legacy of what happened in the 1940s and 50s with waste. And so I'm now trying to put sensors into places with very high gamma radiation and recover the data from those through very thick concrete walls. But interestingly, we've had to go old school. No modern silicon device, even some of the rad-hard technologies, will survive long enough in that gamma field. So would you believe we're building basic radio transmitters at a transistor level, so we're making the feature size of the transistor big enough that it has a life of a few years, And guess what? We're going back to very primitive techniques. So I'm actually going to my students, go to the library, get the radio amateur handbook from 1960, and start reading and using that. And what that means is I need very simple, robust, again, data communication techniques. And my last word, because this is what we did talk about over lunch, was this is one of the problems for me with AI, is if you say to AI, I need a receiver of this type, it's now munging together so many technologies, and we need to help our students become really critical users to understand, and that really means you've got to understand your history enough to know where your answer came from, which means that things like this acknowledgement is so precious to us. Thank you very much.
Thank you, Peter, for an excellent talk. That was really interesting, not being a communications person, to actually see some of these things. Are there any questions for Peter?
Is Milestone code ever protected?
Not that we have found at all. I suspect, I can only say the word suspect, and Jim will know why, is I think it was used in digital comms by the military, in the same way as SPED spectrum was used by the military and protected in that sense. And just in the same way that SPED spectrum then went into commercial use in wireless networks, I think it bled across that way. So I think it was protected, but not by patents.
Thank you. Question here.
Could you just go again, perhaps a little slower, the problem with the AI that you mentioned?
Yes, so, okay, I'll give you an example from a different space. So there's a consulting company called Arup. Some of you may know them, consulting engineers, civil engineers. And I was in their offices, and they showed me a bridge that had been designed by a recent graduate, civil engineer. And what he'd been asked to do is design a bridge that spans a 10-meter waterway, and it's a pedestrian bridge. And what came out of it looked beautiful to my sort of lay view. It was a beautiful arch, tensioned arch, with an infill of a lattice. And the problem was this: when the engineers, there was probably 30 to 40 years experience in the room, looking at it, they said, we just don't know. Because it doesn't conform to a template we know, we don't know what it would cost, we don't know if it's probably going to be strong enough, and we don't know if it's buildable. And when they did a lot of track back, what they found was it seemed to be a blend of a 1960s lattice structure and a 2010 tensioned arch. And you could say, wonderful. But because people didn't know the history of the bridge design, the student didn't, it then meant that the cost of doing an analysis was probably north of about 100,000 in terms of modeling that bridge to work out. And I think one of the problems, I think, is some of the students now were saying this last year, I think they've got like a 5-year window. They believe everything's happened in the last 5 years. And I don't know why 5 years, I can't explain it to you. But it's almost like there's a running window of 5 years. And when you say to them something like Manchester Code, and you was to say 1940s, it's like you've gone minus infinity. You know what I mean? It's sort of like, I don't want them to become historians, but I do want them to have the awareness to understand the derivation path. Because if you understand the derivation path of coding, you understand all the strengths and weaknesses. And that's why, in a sense, I think these recognitions, these milestone recognitions, are really important ways of showing to students points in history where things were understood, discovered, and then the evolution from them. But I do worry that a non-critical use of AI could lead to problems going forward. We've somehow got to educate people to be critical users of it. Use it for its strengths, but learn to be critical users.
Yep. No, that's a really excellent point at which to finish your talk. Thanks very much, Peter. That was excellent. we are drawing this event to a close, and in doing so, I would like to invite Nagan Sigam, hopefully I have not totally mashed that, Chair of the UK and Republic of Ireland section of the IEEE, to say a few words, please.
Yes, thank you very much. So are you showing my slides? Or?
Hopefully.
Yeah. Thank you. So thank you, Tom, and I would like to congratulate you. Am I doing it?
There's a second one as well.
Oh, this one, yeah.
Is that the one?
Yeah.
Okay, great.
Thank you, Tom, and I would like to congratulate the University of Manchester for another milestone. And like Duncan said, you've got a lot of milestones, which we are so proud of. And if that's showing something, it's showing a dedication from the staff to make sure all the innovation that's happened in Manchester is recognized and appreciated by IEEE. So on behalf of the section, IEEE UK and Ireland, I would like to congratulate you. I would like to introduce the section to you. So we are very proud members, and I've got here with me colleagues who really dedicated and great volunteers, and they've been contributing massively to our section, and I worked with them. And really, I would like to encourage you to reach out to them through the reception to ask them a question if you are not a member with us. So I'm sure you've got Nick here, you've got Annabelle here, you've got Rob there, and Norman as well there. And of course, we've got Region 8 representation from Adam, and Tom is there. So the last time I looked at our statistics, we are more than 10,000 members in UK and Ireland, and you can see from the percentage, male to female is not that much, but we are working on that with many activities that we are trying to balance it. And we are so proud, and we consider ourselves one of the most active section in our IEEE. So UK and Ireland, we are very active. Every time we go to Region 8, they give us a lot of compliment of the great work that we volunteers do. So the strategy for our section for 2026-2027, of course, it is influenced by IEEE, but we would like to continue focusing on our innovation, and this milestone is one of the great things that we are very proud of and we appreciate. But also we want to make sure that because of the background of our members, they're all diverse and they are coming from different backgrounds. So we really would like to have inclusion as one of the pillars that we consider in all the activities and all the work that we are doing. And of course, we would like to communicate. We have many societies, and we would love to, the societies, they work together to create a more impactful events for our members. So the most important things for us is our members. So their challenges is an opportunity for us to transfer it to an impactful event or a workshop or a conference. We take this as an opportunity. So our members, if they need our help to become senior members, this is an opportunity for us to create a workshop to support them to make that happen. And so, because most of them, they are there, but just they need the support and the help, and this is one of the things that this section is doing. So I'm putting there a code for you to scan it that will show you the website, which our colleague Nick is looking after. And it will show you more information about our strategy. Another example is just really we'd love to if there is any new topic which really we would like to talk about it, this is an opportunity for us to create a workshop and talk more about it. We've got a good number of technical workshops at our section, around 31 technical chapters. I can see here a couple of chairs who joined us today to support this event. And also we've got 4 technical councils and 3 affinity groups. This barcode, if you go, you will see the societies that we have. This is our website, so you can see the societies we have. So if you'd like to reach out to the chairs and support in any activity or any shape or form, you are more than welcome. For us, we have more than 100 students' branches all over UK and Ireland, and we admit that we don't have many in Wales, and we are working toward that. So I would like to congratulate you again, and you can see University of Manchester in this slide for 3 times. So we are very proud that the team here, they are working so hard, and I would like to congratulate Jim for the hard work he's doing. So from the time this program has been initiated, UK and Ireland achieved 23 milestones, including the one which is going to happen on the 29th of September at Bletchley Park, the Colosseum milestone. And I will end with asking you if you'd like to follow us on LinkedIn. All our activities, we will try to publish it on LinkedIn so you'll stay connected. Thank you very much.
Thank you very much for saying that. I can say certainly from my personal experience, being a member of learned societies such as the IEEE is really something that is quite useful in engaging with your community, developing your profile within a community. So that's something that I can personally, from first-hand experience, and I think from all the speakers you've heard today, would say a similar thing. So it's my final duty to propose a vote of thanks for all the speakers, and in particular for Jim and all his work in leading this proposal. So please, let's thank everybody again. Okay. And now the bit you've actually been waiting for, which is the reception, which is upstairs. It's on our first floor, so it's at the top level here. If you go out of the back of the lecture theatre, you'll be at the right level. Otherwise, if you go out of the lower door, it's a matter of going up a few steps past the stairs where you came in. So thank you very much for coming today, and I hope you found it an interesting afternoon. Thank you.